All right, so we talked a bit about how to process chunks independently in parallel, right? So each chunk runs sequentially, but we run a bunch of sequential chunks in parallel, so we get a speed up. Now we're going to talk about some other aspects of fork join pools. We're going to talk about how to configure them, because sometimes the number of threads you get out of the box isn't quite what you need. And we'll also talk about how to avoid starvation and improving performance by using this interesting thing called a managed blocker. And a lot of what I'm about to describe is not very well known. So this is kind of like the black art, the mystery of streams programming. So let's start by talking about how to configure a parallel stream. So for various reasons, and you can watch Brian Getz's presentation. He's got a nice video that describes some of this stuff. They intentionally designed parallel streams with a very few, if any, knobs to configure and control their behavior. They decided not to give you many things to do. Now, if you want to program at the fork join pool level, you get more. If you want to program at the executor service level, that's even lower level than the fork join pool interface, you get even more stuff, right? So there's all kinds of things you can do if you're willing to put your mind to it. But they tried to make it very simple. And in particular, there's this concept of a common fork join pool. Why do we have a common fork join pool? And the reason we have a common fork join pool is because it allows there to be one location per process where it keeps track of all the work that's being done, and more importantly, one place can decide how to allocate and optimize the placement of work tasks onto the cores. Whereas if we broke it up into smaller pieces, then each part might think it was doing something that was locally optimal, but the overall effect might not be globally optimal. And in particular, we might not end up being able to as evenly balance all the work on the pool of cores available. And this is a common tension, by the way. This is very, very common. So if you think about how the heap works, hopefully when you took, like, if you take either the compiler course or the programming languages course, maybe data structures course, there's some place along the way, hopefully at Vanderbilt, where they talk about heaps and managing free stores. And you know, if you do it right and you have a good heap or a good dynamic memory manager, then all parts of your program can use that, and it can globally optimize the use of memory in the program. However, sometimes people think, oh, you know, I'm smarter than the heap. I can have my own, you know, my own linked list of things, my own free list of stuff. I can manage that locally. And sometimes you're right, sometimes you can't. But oftentimes you can't. And even if you can manage it locally, if everybody manages it locally, then you've lost the ability to globally keep track of all that state. Lots of other examples, you know, in organizations like companies or universities or the government, there's always this tension between letting each of the units manage their own resources versus centralizing stuff, right? And the idea is if you centralize things, you get this economy of scale. The downside is you lose local control. If you have local control, people make local decisions that are optimal for them, but maybe not good for the overall organization, right? So this never-ending tension. Anyway, this decision that's made for fork join pool is along the same lines, right? This trade-off between central and decentralized. By default, the common fork join pool, which everybody kind of has to use for all the parallel streams in a process, has one less thread than the number of cores. So if you go here and you run this program here at this link, you'll see that there's a place where it says forkjoinpool.getCommonPoolParallelism. And I've got a quad-core laptop, and it returns 7. What the heck does that come from? Well, it turns out my laptop is hyper-threaded, so the VM, the Java Virtual Machine, actually treats it as though there are 8 cores. You know, they're kind of virtual cores in some sense, but they're 8 virtual cores. And so the fork join pool, the common fork join pool, uses 7 of them by default. Now, why the heck does it do that? Why does it choose 7? That's because there's also the main thread, and whenever you do things with parallel streams, the main thread is also typically included as well. So the main thread plus the 7 threads in the fork join pool equals 8, which is the number of cores, number of virtual cores. So what that's saying is it's trying to optimize things on your behalf to be smart. However, that's not always the right number, right? 8 or 7 or whatever isn't always the right number of threads to use in a fork join pool. So let's take a look at an example. So let's say I want to download a bunch of images, right? So we've got the image program that you guys are playing around with, and I might want to download 10 images. Well, if there's only 8 threads being provided in the pool, and let's say, I want to download 20 or whatever, these image downloads are going to block. And when you run your little visualizer that you now have, you can see the effect of blocking, right? One of the effects of blocking is things tend to take the thread away and nothing else can run in the meantime, even though most of the time the threads may be blocked in image downloads, and therefore if there were more threads, they could make progress. Does that make sense? So this is one of the key things to remember when you have an I/O-bound program, and obviously image downloading and filtering is pretty I/O bound, or parts of it are pretty I/O bound. The downloading part's I/O bound at least. If I have, let's make it easy, let's say I have 4 cores, if I only have 4 threads available to me, but 10 images to download, at any given point, all 4 of those threads will be blocked in I/O. But when you're blocked in I/O, that thread is taken out of the pool. Nobody else can use it. Now, while you're blocked in I/O, the operating system will actually say, I'm going to put that thread to sleep till the I/O is done. And if there is another thread, I'll let that guy run, right? So maybe there's another thread that could be doing some image processing, which is a CPU-intensive task, not an I/O-intensive task. So if I only have a fixed number of threads and I stick with that fixed number of threads, then I'm going to have a less optimized program. And the fancy way of saying that is I won't be able to leverage the inherent parallelism in the program. There's inherent parallelism in the program that's not being leveraged as a result of this. So I'll either end up with underutilization, or I could even have deadlock in some cases, depending on what the program's doing. All right, so what's a better way to handle this? Well, one thing to do is if you really do, in fact, know the number of things that are going to block, like the total number of things that are going to block, like 10 images or whatever, then you can do the following. You can actually set a property, a system property, and say, I want the parallelism in the fork-join pool, the default fork-join pool, the common fork-join pool's parallelism to be n, where n is whatever you think the maximum blocking might be. Okay, so that's better, right? We could set that. If we know we're going to download 10 images in parallel, let's make this 10. The downside, of course, is that this property, setting this property, affects all the parallel streams in a process. Now, if you're making them bigger, it's probably not the end of the world. But if you, for some reason, were to make it smaller, then you've just taken away more threads that could have been used by other parallel streams that might be running in other parts of your program. So the metaphor here is there's a ripple effect, right? So it ripples across and causes, cross-contamination, if you will. So the thing to remember here is if you know precisely how many threads you need that will block, this is one way to do it. But it's often hard to estimate this, especially if you have a program that's dynamic. So what would be an example of a dynamic program? Well, anything that's going out and downloading, say, images on a web page. You don't really know until you see the web page how many images there are, and you don't really know until you traverse all the web pages reachable from that web page how many images there will be. So it's very hard to estimate, and you don't want to keep setting this property higher and lower, because if there's other things going on, chaos and insanity will reign, and undoubtedly you'll get it wrong, right? So it's just a bad thing. So what can we do? Well, what we can do instead is we can use something called the ManagedBlocker class. And this is a very it's well documented, poorly understood, or poorly recognized aspect of Java fork join pool and parallel streams. Very few people know it exists. You'll see lots of learned articles that give you all this advice about how to deal with parallel streams, and they don't understand this feature, and so they just make all kinds of bad assumptions, which is always kind of funny. So ManagedBlocker is a way to be able to tell the fork join pool to temporarily add worker threads to the common fork join pool. So it'll add them for a period of time. So it'll add them as long as they're being used, and once they're no longer being used, as we'll see shortly, it goes ahead and shuts them down. So this is particularly useful for behaviors, for tasks that have to block on I/O and or on synchronizers. So anytime you're going to block, this might be for you. And I'll show you some code later that illustrates how all this stuff works. But the bottom line is take a look at the image stream gang to see how to use this. It's actually quite simple. And it's actually in your, I think it's in the skeleton code for your assignment 2, the parallel streams. If you look, there's a thing called blocking download image, or blocking image download, or blocking download. And it uses this under the hood. So let's talk a little bit about this interface. So the ManagedBlocker is useful when you have use cases where more worker threads are temporarily needed in order to ensure the liveness and responsiveness of your program. So, right, if you have bursty processing where you suddenly have a lot of work, but then it goes away, this is really good to be able to handle that kind of a scenario. So what it does is it automatically and temporarily increases the common fork join pool size. So we could use this, for example, in various places. We can use it both for the conventional fork join pool kind of stuff, as well as for parallel streams. So it works nicely either place. We're going to use it, obviously, for parallel streams here, but you could use it if you're writing at the lower level. And then the fork join pool is very, very cleverly implemented. I'll show you some of the implementation stuff later, to reclaim threads when they haven't been used for a while, right? So basically, it'll either, if they're used for a short time, we download a bunch of images, and then we're done with the IO-bound part of the program after we've downloaded stuff, then it'll just basically kill those threads. But if you go through bursts, right, you go through phases where you need a bunch of IO, then you don't. Then you need a bunch of IO, then you don't. It'll actually kind of park these things in a clever way to be able to quickly reinstate them. So it's kind of like the, let's see, it's a Hindu concept or Buddhist concept of samsara, right? It's the cycle of life and death, and so it reincarnates the threads efficiently. Basically, what it also does, fork join pool will try to ensure the target parallelism level is met. So it behaves like a control system where it's keeping track of what it wants, seeing what is obtaining, and then has a feedback loop to add and remove these things. The way this works under the hood is by an interface called ManagedBlocker. And there are two methods. One is called isReleasable, and this returns true if blocking is not necessary. So if you got the resource and you're done, this is particularly good for things like locks, then isReleasable will return true, and then there's no need to block, there's no need to allocate any more threads. There's also a method called block, and block may block the calling thread. Now again, it all depends on how it works, but this depends on whether or not you acquired the lock or the IO operation finished quickly. So block will essentially block, potentially, and if it doesn't end up blocking, it returns true. Kind of funny, because you'd think block returning true would mean it blocked. But if it returns true, that means it didn't block. And if it returns false, that means it blocked. And I'll show you how this actually gets used. So let's see how this thing works under the hood, right? So this is a snippet of the fork join pool implementation. So if you really want to go the way of pain, with Gandalf living on top of Orthanc in a rainstorm, go ahead and read the fork join pool code. It's super duper optimized, almost impossible to read, but it's cool. And here's one of the methods called ManagedBlock, and you can see ManagedBlock takes a ManagedBlocker. And this method, ManagedBlock, will activate a spare thread, and we'll see how that works here in a second, if needed, to ensure that there's enough parallelism while the calling thread blocks doing its thing. And so here's the way this works. So while we have to block, or while we didn't get what we wanted to, we call try compensate. Try compensate is an incredibly complicated method that checks to see if there's any live threads, and if there aren't enough of them, it creates or reactivates a spare thread to compensate for the blocked thread until it unblocks. So that's what try compensate does. And then down here, we have isReleasable and blocker block, and this might actually block the calling thread. And so if that blocks, then hopefully try compensate will have allocated threads to keep things going while this guy blocks. Really complicated, as you can get a feeling for. Not that hard to use, hard to implement, so thank goodness you don't have to implement it. So here's one way to do this. This is a simple implementation called ManagedBlocker, which is a funny name. So ManagedBlocker implements ManagedBlocker, and you can read the Java documentation to see how this works. And that's going to handle a blocking synchronizer. What the heck is a blocking synchronizer? A blocking synchronizer would be something like a semaphore or a reentrant lock that might need to wait to acquire a resource. What's a good example of this from everyday life? If you've ever flown on an airplane, then you know that they have an airplane lavatory, and the rule is when someone is in there, the little sign says occupied and the door is locked, right? And if you want to get in, the protocol is you have to wait by the door until it's unlocked, and then the person leaves and you can go in. So there might be some blocking involved. And if you ever fly in an airplane, they always say, do not form a line at the front of the plane or something like that. So we're assuming this is the lavatory in the back of the plane. So ManagedBlocker will have a constructor that simply stores the lock that we want to manage. IsReleasable will try to acquire the lock. So there's a try-acquire or try-lock method which will try to get the lock, but if it's not available, then it fails. That's kind of like getting up to go check the restroom, discovering the door is locked, and just going back to your seat, right, rather than standing in line. So that's what try-lock does. Block is implemented by first checking to see if we already have the lock, and if we don't have the lock, then we actually go ahead and block, right? We've tried everything we could do to do non-blocking acquisition of locks and seeing if we've got the lock, et cetera, and we finally say, okay, I have to go, right? I've got to go to the restroom. I'm going to stand in line. So that's what we do here. And so that's obviously going to block until we're done. Let's take a look at how we can use this thing to write code that makes it easier to work with the ManagedBlocker. And this is a really cool little helper class. You can take a look at this example to see how it all works. This is called blocking task. And this uses some neat Java 8 features, some functional interfaces like suppliers and so on, in order to make the ManagedBlocker interface easier to work with. So we have something called blocking task. We have a method called call in ManagedBlocker, and that allows us to use blocking suppliers with a common fork join thread pool. So you can see we're going to pass a supplier into this thing. And then we go ahead and make ourselves a little helper object that holds the supplier. So it's stuffed away somewhere. And then we call fork join pool.manageBlock, which was that function we just looked at, and we pass in the ManagedBlocker. And what will happen is this will block using all the cool stuff under the hood to make sure that it compensates by allocating more threads, et cetera, when this thread blocks. And when it's all done running, then we go ahead and we get the result, and that gets returned. So we can make a very nice generic piece of code. All this stuff is plumbing to run this supplier efficiently in a blocking operation that doesn't cause problems by stealing threads overly zealously without recompensating somehow. Here's the supplier ManagedBlocker. That's this class. That's the helper class. That implements ManagedBlocker. And it's got a bunch of little things. Keeps track of the blocking supplier, keeps track of whether we're done. And then what we do here is we go ahead and initialize this in the constructor. And as you can see here, when block gets called, we're going to call mSupplier.get, which will essentially block to do its work. It's whatever you told it to do. Remember, with the supplier, you provide a lambda or a method reference, and that is turned into a call to get. And this call will then do whatever lambda or method reference you passed in, and that will then work in the blocking context. When it's done, it'll return the result, set the flags appropriately, and then we can get the result later. So super cool, simple little example demonstrating how you can wrap these classes and make them work more effectively. If you take a look at this example, example 20, you'll see how to do it. There's a method called blocking download here. And what this does is it goes ahead and, at a high level, it transforms an image by transforms a URL into an image by downloading the image based on the URL. And the way that works is it calls blocking task call in ManagedBlocker. And notice how it passes in a supplier reference. So this is the lambda supplier, and that's the method that'll get called back by supplier.get, right? So that will end up, this call in the framework that we wrote here as a helper class will get called using this Lambda supplier. So isn't that really cool, right? Now we can write this code that looks just like any old kind of Java 8-like code where we say, hey, here's a Lambda, it downloads an image. I need it to be done in a way that will respect the characteristics of the fork join pool, ... We have a little helper class called blocking task. We give it a supplier, and then it arranges to run that thing in a thread in the pool without taking away from other threads that could be used. So it uses the ManagedBlocker interface to do all that stuff. So super cool mechanism, really easy to program, and the mechanism itself isn't that hard to understand. As we talked about before, if you go through periods of bursts where you have lots of I/O, and then you stop needing I/O, these threads that were created by the try compensate mechanism in the thread, the fork join pool, will then automatically be shut down later when they're not used. Okay, any questions about that?